So good afternoon, everyone, and welcome to this 14th session of CIIPS course. And before we start today's session, let us review what we did in the last class. So what was it that we were discussing in the last class?
Physical contradictions.
Physical contradictions. What are physical contradictions?
When you have two conflicting requirements on the same parameter.
Two valid conflicting requirements on the same parameter.
Same parameter.
Yeah,
like the boat had to be small and the boat had to be large at the same time.
Yeah, great. So how do we solve physical contradictions? There are three ways to solve it.
Three ways, yeah. First way was if we can find a way to space them out in space, time, or relations, something like that. I mean, there are four things. And then the second option was that if you can't do this, then if you could live with the contradiction, I think. And the third was that if you, and the third was that if you, that was something which was, some very like if you can let go of the contradiction or something like that.
Yeah,
it was more.
The first set of solutions is around separating the requirements. We separate the requirements in terms of space, in terms of time, in terms of relationship, in terms of system, microsystem level. So then if you're not able to solve it through separation principles, then we see if we can satisfy both the requirements. If we are not able to do that, then we say, okay, we'll bypass. So bypassing requires a complete paradigm change, a paradigm shift. And we go in this order. Why do we go in this order specifically? Why can't we just do anything? Why can't we just start to think of bypassing first and then think of separating?
To reduce the cost and complexity.
Because when we think of bypassing and a paradigm shift, then the entire supersystem components and the interactions with the supersystem components can also change. That may mean that the overall cost of implementation can be very high. It is a disruptive change that we are talking about. Whereas until we are talking about separation principles, until we are talking about satisfying the requirements, we're trying to keep the cost of this innovation, this invention, as low as possible. We want to just get the job done without really bothering about too many things around it. Okay. So any questions from yesterday? Or even before that, any questions from technical contradiction matrix also? When we are talking about the methods or solution finding methods or even function oriented search. So until now, we've looked at applying function oriented search for finding solutions. We've also looked at using inventive principles. We've looked at using inventive principles in two ways. First is by using technical contradiction matrix. The second is by applying the physical contradictions and solving those physical contradictions. So any questions still here in the solution finding methods? Okay, so there are no questions. Then we look at another solution finding method, which is standard solutions. The name is standard solutions. Why do you think it is called standard solutions? We've discussed this earlier. I just want to see if you remember. Why is this called standard solutions? Is standard solution? Yeah, please.
So based on various previous problem identification stage, looking at various interaction and things like that, it uses actually the inventive principles only to come up with the solution. I mean, that were already defined by for a
Okay.
particular set of problems.
So you're saying that the template of the solutions is inventive principles. That it will tell us inventive principles to be used to solve the problem. Then why is it called solutions? You remember the orange orchards problem and the problem with that boat which had whose base was getting torn, degraded, and we said they are the same problem in Trey's language. Remember that example?
Yes, sir.
So what's happening there? We have taken the problem statement to a much higher level of abstraction. So today we are looking at standard solutions here. And what we are saying is that, you see, to solve a problem, there are different levels of hierarchy. We are going to a very high level of hierarchy to solve this set of problems now. So high a hierarchy level, so high a level of abstraction that in total there are Altshuler defined a total of 76 generalized models of solutions to all engineering problems. See, come to think of it, initially he worked on technical contradiction matrix. How many parameters on the x and how many on the y-axis? 39 each. So how many different kinds of problems are we talking about? Something like 39 into 39?
Yes, sir.
Then we came to physical contradiction matrix. In physical contradiction matrix, how many are we talking about? In physical contradiction matrix, how many methods are we talking about?
So 3 ways, 3 different methods. Or
Three
depending
different.
on them, we have different solutions. Like.
So we are still, the solutions are still amongst those 40, but we are saying that, okay, we will try to solve them through either separating or satisfying or blah, blah, blah. So that was what was done to the physical contradictions. But in that also, there was a significant possibility that many more problems could appear. You had physical contradictions which could be between any two components and any parameters of various components. So the overall multiplicity of the problems was still big. Over here, Altshuler is saying that the entire gamut of engineering systems, all kinds of problems, there are only 76 possible ways to solve them. A total of 76 possible ways to represent those problems and solve them. And then there are standard solutions to those 76 ways. So it reduces your solution search very significantly. Now all that you need to identify to solve the problem is possibly those materials. That's it, nothing else. So let me just move to the presentation. Give me a second. You able to see my slides?
Yes, sir.
So he says that there are a set of 76 generalized models of solutions to engineering problems. And that is where he says that, we use the language of substances and fields, and the substance field model represents the problem and the solution format. So we discussed this, that just like there is a language in maths, algebra, or trigonometry, or so on, language in chemistry, in terms of chemical equations, language in semiconductor physics in terms of band diagrams, and so on. All of us have studied these languages. In exactly the same way, there's a language for inventive problem solving, which is substance field diagrams, where any problem is represented as interaction between substances and fields. There is a legend: if you have a desired effect, you use a solid arrow. If there's an insufficient desired effect, the same terminology or the same thing that we were using in the function model, dashed arrow. Harmful effect, okay, there we use the red colored arrow, but over here he says just wavy arrow. And then operator, okay. And the kinds of fields that we're talking about are mechanical, acoustic, thermal, chemical, electrical, magnetic, all those fields. So what is a substance field? A substance field means a system formed by interaction of substances and fields. Substances, as we already agreed, are components in the engineering system having rest mass. A field can be considered as similar to energy in a broad sense. It does not have a rest mass per se. Fields are like mechanical, electrical, magnetic, so on. When you apply these fields, the interactions between substances also can get streamlined. Remember the example of ball bearings going through a pipe?
Yes, sir.
So all that was done was we applied a magnetic field here, ball bearings got attached here, and that would solve the entire problem. The pipe would no longer break that frequently. So an effective engineering system must have at least two substances and one field. The field establishes the interactions between those substances, and the graphical representation of their interaction is called the field model or the substance field model. There are 76 problem types or solution types, which are arranged in 5 major classes. The first class, for example, is building and destruction of substance fields. So building and destruction of substance fields has 2 subclasses containing 13 solutions. But that pipe example, over there, what was happening? There were 2 substances, but no field there. So the solution was adding a field. That kind of a problem would come under category 1. Okay. Then development of substance fields. What does this mean? This means introducing modifications within the boundaries of the system. It has 4 subclasses containing 23 solutions in total. And you remember this orchard example where we said that the modification of oranges, which is lemons, should be planted at the periphery of the orchard. So what was happening? If you remember the substance field there, there was an optical field there, monkeys and oranges. Monkeys and oranges were interacting through this field, and this interaction was harmful interaction. You remember this? You remember the problem?
Yes, sir. Yes, sir.
So what did we do? We said, okay, we will modify this field. We will add lemons in between. So monkeys now only see lemons. They don't see oranges. They taste lemons and they go out. That is you have developed the substance field by adding another substance. Then transition to super system or micro level. We will see an example of that, I think, in the few slides. Then standards for detecting and measuring. How do you, so see, many a times you will notice that many of our problems are about detecting and measuring. You want to detect when the cache is about to be full, or when for that paint filling thing, when the paint paint is almost there. You want to measure that, or you want to detect that when the paint reaches this level, I want to detect and I want to stop the motor. In your work also, you will notice that many times you want to detect how the user has responded or what is the impact that your system is making, and then you want to modify the system. So there are 5 subclasses in which 17 solutions are organized, and these are standards for detecting and measuring. If you are facing a problem where your detection or measurement things are not happening properly, these 17 solutions can come in very handy. And then the last category is standards on application of standards. So these are the standards, these are the standard solutions. How do you apply these standard solutions, in which sequence and all that? And over there again, there are 17 solutions there. Okay. This is in fact a method to achieve the ideal final result. So ideal final result, what do you think this means? What do you think? What do you think this phrase "ideal final result" means?
It eliminates a problem. I mean, facilitates the destruction of or creation, like in the first example.
So we want that nothing should be added, like minimal addition, or actually, for example, in that the steel ball bearings problem, the ball bearings themselves organize themselves, or ball bearings organize themselves so that they don't damage the pipe. That is the ideal solution, no? Or in that paint filling problem, the paint automatically stops when the tank is full. That is the ideal solution. I don't need any additional paraphernalia. So the work gets done with no extra energy, no extra cost. That is the ideal solution. If there is a cost involved, can the solution be ideal? No. Ideal means zero cost, but the answer is there. So the 5th class of solutions is about how to achieve ideal final result. In which situations you can target achieving ideal final result. The work gets done with no extra cost. Interesting, no? So when a field in a substance field model is missing, the following fields can be considered. In fact, I remember it as a term called MATCHEM. Mechanical, acoustic, thermal, chemical, electrical, magnetic. So MATCHEM is what we call this as. Now this is for generic engineering problems. You will notice that it comes in very handy. For those of us who are electronics engineers or who are computers engineers, we may want to say that, okay, for us, the things are limited to probably electrical, magnetic, thermal at times. When we talk about micro electromechanical systems, MEMS, then also mechanical. But unless you're talking about microphones or something, acoustic will not usually come in. Unless you're talking about specific sensors like gas sensors or particle sensors, chemical may also not come in. Okay, so typically we will be dealing with electrical, magnetic, thermal, or mechanical in our systems. So yeah, this was the problem that we were talking about. Over here, the balls were interacting with the wall, and the wall was getting ruptured very frequently. We realized that there are 2 substances interacting amongst each other. The substance field diagram is not complete, and we wanted to add a field. And since we are talking about steel balls and steel pipe and everything, magnetic field is the natural choice there. You remember this example?
Yes, sir.
Yes, sir.
Great. So this was the other example that we've been talking about till now, where we had hydrofoils which would get eroded because of air bubbles, and monkeys would, spoil the orange plantations. So there are 2 things interacting in a harmful manner, and what you did was you introduced a modification. For the hydrofoils, you said that you would modify the form of water so that you have ice. So air bubbles will cavitate on the ice. They will not erode the bottom of the hydrofoil. And in terms of orange plantations, you plant lemon trees across the boundary so that the monkeys don't even get to see the oranges, and the plantation is saved. Again, this problem, I think all of us remember now. Now, how do you measure? Now, I'm coming to the class 4th because, as I said, a lot of our problems are about measurement and detection. If I have to measure the length of the snake and the snake is alive, how would you measure it? There's a snake and I want to measure its length. How would you measure it?
Using some sort of paint, and I mean, we can see the area. I mean, like there was a simple example when we were in class 5th, how we check the circumference of a circle.
Mm-hmm.
So in that case, we just use a thread and wrap it around the circumference to see what the length of the thread is. So we can use a similar approach, I guess.
So the snake will bite you as soon as you go close to it and start to, okay, you may start with the tail, but finally you will have to take the thread to its head.
Sir, allow it to move through a tube. That's a predetermined length.
So allow it ka matlab kya hai? There's a snake right there in front of you. What do you mean by allow it?
We'll put the pipe or something in front of the snake, the length, so that we can as it travels, we can get some idea of how long it is.
Yeah. Okay. More ideas? So one of the standard solutions is use a copy of the snake, of the thing that you want to measure. For example, you would have heard about those of you who are not circuit designers. I don't want to bother you with that example of canaries, but use a copy of the component or the system to do the measurement. So what would be the copy of the snake?
Sir, a rope.
A rope. A rope is a copy of the snake. Okay, so something else? Rope se to finally, rope you will use as a thread, na? You will want to measure the rope finally. But yeah, Parth?
So a copy, I mean, would it be a match-to-match copy? That is, can the size be different?
Yeah, scaled copy chalega.
No. I mean, can we use a worm in that case? Not.
Interesting. सोचो कुछ. There's a snake. I want to measure its length. What could be a copy? Do snakes have a property through which you can measure their length? Do snakes leave something behind them, a copy of theirs behind them?
Yes, sir.
Shed their skin.
Covering their shells.
They shed their skin.
Yeah.
So if you can get hold of its skin, which it had recently shed, you just have the copy, you can measure it. Or another copy could be you take a photograph. That's a copy. So, okay, the major recommendations are try to change the system. There is no need for measurement, or measure a copy. Introduce a substance that generates a field. So introduce a mark internally or externally, or build a measurement substance field. So copy the snake. And this is the skin of the snake that we could use. Or you just place a ruler somewhere so that you get the scale, idea of the scale, and then you take a photograph along with the ruler. Now you just use the thread on this photograph and you will get an idea of So this photograph, because of the cellophane film, you are not able to see the entire winding of the snake. So you'll have to use the rod or the something to make it unwind itself so that you're able to do it. But you keep a ruler there and take a photograph, and then you can measure the length of the snake. Does this help?
Yes sir, but sir हमेशा तो अवेलेबल नहीं होगा ना. I think like snake ने shed करी है अपनी like skin अभी.
So
that's a problem.
So snake की length measure करने की requirement कहाँ पे आएगी? चलो ये let us look at that. Where would you want to measure the length of the snake? In which settings?
Sir, I think अगर हमको मिल जाता है कभी ऐसे ही like घर में or something.
तो तुम उससे भागोगे, उसके length measure करोगे?
नहीं sir, I mean like we can tell people कि like that his size was this or something.
Okay.
So to monitor growth maybe.
Sorry?
To monitor its growth maybe, where the skin
So where the snakes are being reared, for example, for some purpose, either to collect their venom or to do something. So when you want to study the snake, for example, or you are studying, doing something about those your hand. So snake की length measurement करने की problem usually तब है जब आपको उससे कुछ लेना देना है, ना कि बस डींगे मारनी है पड़ोस में कि मेरे घर में इतना बड़ा सांप आया था. So अगर वो डींगे भी मारनी है तो जहाँ पे वो सांप खड़ा था उधर की वो उसके भाग जाने के बाद उस लेंथ को मेजर कर लेंगे हम. हाँ, तो वहां पे तो उससे हो जाएगा काम. लेकिन otherwise, this requirement typically comes when you are rearing snakes or when you are kind of doing a study on snakes and their growth or something like that. In that case, you will on a very frequent basis be able to get its shed skin, because as the snake grows, it will shed its skin. And if the skin has been shed just about, say, even a few days back, you will be within 1 centimeter of the actual length of the snake. Otherwise, you just take a photograph like this one. This one was taken in a setting where venom was being collected. And then you will be able to estimate the length of the snake by using a thread over this photograph there. So there are many other examples of how substance field, how systems are modified to prevent use of or to prevent any measurement at all. I remember, so you remember, try to change the system where there is no need to measure or detect. So there was I remember a case study where there was something, there was a circuit which was to be broken. So there was a heater circuit, and we wanted to break this circuit as soon as the temperature reached something like 67 degrees Celsius. So what was done was that the switch was made out of a magnetic material, and as soon as the temperature reached 67 degrees Celsius, so the magnetic material had the Curie point of 67 degrees Celsius. So as soon as the temperature reached 67, the magnetism was lost and the switch would close. Okay, so now because you've used a material, now you don't really need to measure the temperature with a thermometer. So everything else is not needed now. The system has been modified so that there is no need to measure. The system will automatically operate. I also remember an example where, for example, you want to detect leakages in a refrigerant. Big refrigeration systems in industrial settings, the refrigerant is leaking. Yeah, big systems. क्या आपके घर पे भी, you have these split ACs, the refrigerant may leak. So you want to detect that. How do you do it? How would you detect the leakage in a refrigerant?
Monitor the pressure.
Oh, to monitor the pressure, then you have to have a pressure gauge and everything. आप घर पे हो, you want to just, you want the system to tell yourself, then you're measuring, then you're essentially measuring. we want to avoid measurements. Because measurement is the problem. ना अब घर में कितनी जगह से पाइप घूम रहा है. How do you measure everywhere? How do you locate where the leakage is happening?
Gas, if the leaking gas is having some order, like in LPG, like they added, I don't remember the name of that gas.
Hydrogen
It was
sulfide. Hydrogen sulfide.
so as to detect whether there is any leakage or not.
So that prevented, so adding that hydrogen sulfide ensured that what field was generated? Olfactory field was generated. You could smell it now. In terms of refrigerants, you want an optical field, preferably. So what is done is, in big systems, the gas is actually also mixed with some fluorescent substance. A fluorescent substance is added to the gas. So wherever the gas is leaking from, even if it is a very dark crevice, you just run the torch to see is there any leakage. And if it is leaking from somewhere, that part of that hole, chota sa bhi hole hoga, because of the fluorescent substance, it will at once shine. The substance will itself tell you, the hole will itself tell you, I am here. You just need to go and plug it. So you've added a field so that you're able to solve the problem there. So this is a quick overview of substance field diagrams and the standard solutions. I don't think we will be needing to use many of them. I think for most of our purposes in our course, use of the technical contradiction matrix, the physical contradictions, function-oriented search, etc., would be able to help us solve the problems. Okay, so I will keep this session to this introduction level only. We can go in more details. If you want, I can point you to resources where you can have much more details about standard solutions. But for the purpose of this class, we will limit it at this. Is that okay? Is that okay?
Okay, sir.
What option do you have? You can't even say no. If you say nahi hame aur padhao, to then there is more material to study. If you say कि नहीं पढ़ाओ तो भी आपके पास ऑप्शन नहीं है, इतना तो पढ़ाना ही है. ठीक है. So I think in terms of substance field diagrams, the first step is to translate the initial engineering problem into one of the typical substance field models. And then the next step is to identify the applicable generalized solution. So we saw that, okay, there is a substance field model which is like this. We understood it, a field is missing. So we would add a field which would interact with them. So that is the generalized solution. Now, for this generalized solution, we had to identify what is the field, what is the specific technical idea for solving the problem. We said, put a magnet there. For the monkeys thing, we saw that there is a field that is interacting and then the two substances interacting and it is harmful. So we made the typical substance field model. The typical solution to this is where we say that a modification of either S1 or S2 will be added to the system. And that was how we solved it. Then we saw what is this modification of S1 or S2. And we saw that there were two ways to modify, for example, the monkey problem. The first was we would use lemons. So we modified oranges and we are using another citrus fruit, which can grow in the same region, in the same climate, which was lemons. What was the other modification that we had thought of? How would you modify monkeys? We talked about that also. What is the modification of monkeys that could be used? Huh? What is the modification of monkeys that we could use there?
So apes, I think you said something about big apes like langurs.
Yeah, we said we would use a langur. because langurs scare the monkeys away. They would not let the monkeys come close to the orchard at all. In fact, langurs are the solution which are used in in the central Delhi region, where the north block and the south block that are close to the parliament, they were heavily infested with monkeys. So the government actually had to hire langur keepers. So these langur walas would come and they will just move around in that area, and the monkeys would run away. So the monkeys were then taken away and deported to the Asola sanctuary over here, Asola Wildlife Sanctuary over here in South Delhi. But langurs were the solution that were used by the by the central government there. So again, as I was mentioning, the power and uniqueness of the standard solutions is that first it is based on analysis of millions of patents, and it says that almost all the engineering problems can be modeled in terms of these substance field structures, and there are 76 solutions. So it significantly reduces the time for problem solving, or significantly improves your problem solving by reducing the number of potential ideas that you need to consider. So the ideality of your solution finding becomes very high. Are you able to see this? Instead of a 39x39 matrix, or instead of applying so many different ways of trying to solve separate and then satisfy and then bypass, there are standard solutions straight away. It reduces the scope of your solution search significantly, saves a lot of time. As I mentioned, the key terms are that there are 76 typical solutions. A SU field model or a substance field model is a symbolic model of the problem or solution formulated in terms of interactions between substances and fields. The difference between a substance and field is that substance is an object with a rest mass. A field is an entity without rest mass that transmits interaction between substances. So olfactory field, optical field, acoustic field, all these are fields. Magnetic, electrical, everything. These are all fields that transmit interaction between substances. So with that, we will stop the instruction part of today's session, and we will enter into the breakout rooms. You can continue to work on your project problems, and if there are any questions, I would be able to help you by coming to your rooms. Any questions about the substance field diagrams or substance field models before we break out? Okay, so if there are no questions, let's enter the breakout rooms. And yes.
Yeah, if you could please enable the share screen option.
Oh yes, just give me a second. All of you will be able to share now.
Thank you.
So I'm opening the rooms. So I still see that there are people who are not assigned to some room. So let me just put you in your teams. So Aman, which room are you in? Which team are you in?
Sir, 11.
11.